Okay, now you will find that if the material is being wasted in the region close to the neutral axis, then why not make beams save money, make the structure the beam more efficient? We can do that, and that's how this concept of I section came. Because the more you spread out the material further away from the neutral axis, the greater the benefit, the greater the I. After all, you're paying for the material, you're paying for weight, you're paying for volume, you're paying because the density is the same, you're paying for area, how it's distributed. So let's take two sections now. One is rectangular, the same section we saw earlier, width A and depth 3A, and the other we will spread it apart by a distance 3A, so the overall depth is the same, but we increase the width also to 3A, just as an example. And each of them has a thickness of 0.5A spread apart and interconnected somehow. Okay, usually these two are called flanges. This is called the web, and the web can be very thin. We'll see later that the flanges resist the moment, like in a truss, and the web resists the shear. So both A and B now have the same total area of cross section 3A squared. They have the same weight more or less. You're paying the same amount. But now if you work out their efficiencies using the same method, and I suggest you do this yourself. I'm going to go fast. I leave it to you to work out these calculations. ZA is what we got last time. For ZB, you have to do a bit of calculation. I presume you know how to calculate. You have to use what is called as the parallel axis theorem to find the second moment of area of two areas about some other location. So each of these flanges has its own second moment of area, BD cubed by 12, 3A into 0.5 A cubed by 12, and there are two of them, so into 2 outside. Then each of them has a contribution AD squared. If you remember, the area is 3A into 0.5 A, and the distance from the centroidal axis is actually, you have to get it to the centroid of this area, so it's 1.5 A minus half of 0.5 A, the whole squared. You work this out, you get something as a function of A raised to 4. And then to get Z, you have to take Y max, I by Y max, and you get something. If you compare these two, you can show that the I section is more than 2 times efficient compared to the rectangular section for this choice of, for this example problem. So that's why I sections are said to be more efficient, less deflection, more strength. Okay, so the bending moment capacity is 2.11 times. You could get simple questions like this to test your understanding. I have just one slide on shear stresses because it's outside the scope of our topic, but you should know it. Till now we looked conveniently at problems of pure bending. Pure bending means the bending moment is constant throughout the length. The curvature is the same. All points along the length of the beam have the same radius of curvature, but in reality that will rarely happen. So let's finish this. Let's look what's happening. Let's take points along the depth of the beam, and the state of stress of these 5 positions are very simple. At the neutral axis there's nothing, and then you'll find there's compression further away from the neutral axis and tension further down the neutral axis, right? Linear variation. We saw this. Now what happens if there is shear and the curve and all bend in parallel lines, and the neutral axis, which is the centroidal axis, will have a radius of curvature r. The others will either increase or decrease depending on y. We know that. What happens when you don't have pure bending? In pure bending, the stresses and strains are linearly distributed. If you have shear, for example, instead of a moment at the free end, I am now applying on the cantilever beam a concentrated load, and that too distributed along the face of the beam. In practice, I may apply it above or below, it doesn't matter. What's going to happen? Well, if you take a look at all those 5 elements once more, you'll find that to satisfy equilibrium, you have to have shear. And you have complementary shear. So shear can happen in both directions. You've studied this. At the neutral axis location, you will have only shear. You don't have any normal force. And what does this shear do? The shear is going to distort that section. The rectangle will no longer become rectangle. It will warp. It will get distorted. And you can see clearly that pure shear is a case of one diagonal getting extended and the other diagonal getting contracted. So pure shear can be also looked at equal tension and compression across perpendicular diagonal directions. So that's very interesting. And if you look at other locations, you'll get some distortion, but not as much as here. And so if you look at what happens to the plane sections, they no longer remain plane. You'll have a little warping. This is important to note, and the warping can be significant. It depends on the span to depth ratio. For deep beams, it will be quite significant. But for normal beams, we ignore this warping. And it's also important to note that the shear stress is actually maximum. In a rectangular section, you'll find that it's a parabolic distribution. This can be derived with a peak exactly where the bending stress is 0. Very interesting. Where bending stress is 0, shear stress is maximum. Where shear stress is 0, bending stress is maximum. The shear stress is 0 at the top and bottom because at the top, exactly at the top and bottom, you have a free surface. Remember, shear comes from friction between the layers, the horizontal shear. There's nothing to rub against at the top and bottom. So the shear stress has to be 0 at the top. We leave shear in peace there. We don't distort our understanding by including shear. Let's come back to bending. So we'll now go to the next topic, which is very important. We have to master this. Given any beam, and let's say statically determinate beam, could be cantilever, could be simply supported, could be propped cantilever with an internal hinge, could be a complicated system with a lot of internal hinges like the balanced cantilever bridge we saw. We should be able to crack it. And you must master this. You must be able to draw shear force and bending moment diagram for any beam, statically determinate, and also related to the deflected shape. So let's do some examples. These are problems. Let's do them together. Okay. Please take down this problem. What is this called? This is called a beam with an overhang. Okay. Incidentally, if you have any doubts, you could send a message and we'll clarify it. But this is a beam with an overhang subjected to a point load or a concentrated load at the middle of the simply supported region. This is actually an easy problem, but based on the interviews we've conducted with so many students over the years, we find that students tend to trip when they see this problem and they get nervous and draw all kinds of diagrams. The standard question asked is, can you draw the shear force diagram, the bending moment diagram, the deflected shape? Simple question. So let's see how this can be done. Normally, students will calculate the reactions first. In this case, it's very easy. You can guess the reactions. The reactions will be, the 20 kilonewton will be shared. You get 10-10. I hope this is clear from the last lecture, simple equilibrium. You will also note that BC is really, it's an unnecessary addition to this problem, but deliberately given to confuse you. Okay. But let it be there. Whatever you do, you'll get VA equal to 10, VB equal to 10, satisfying equilibrium, symmetry is there. What makes it unsymmetrical is the overhang BC. Then you draw the free body diagram. The free body diagram is a diagram in which you have only arrow marks, no support condition. And so you'll write 20, 10, 10. And then the conventional way at any section X, you have to write down expressions for shear force and bending moment. So you take a free body. You can draw two sections. One is to the left of that load and the other to the right of the load and in the overhang region. So if you take the first section, mechanically you draw two things first. Once you draw this using our sign convention, you draw V and M. V and M. This is our sign convention. Positive sign convention for V, positive sign convention for M. Just do it. And I showed you in the last lecture, you could take either from the left side or the right side, but we'll skip the right side here. You have to satisfy equilibrium. And straight away you know that to satisfy equilibrium, Vx must be 10 and it is pointing downward because sigma Fy will be 0. And moment M, this 10 and this 10 form a couple which acts clockwise, which must be neutralized by this bending moment M acting anti-clockwise, and so that's 10 into X, 10 kilonewton. You need to do just this, but if you want you can write equations, but we don't want to waste time. Simple. Next, let's cut a section to the right of this load. So it will look like this. Now in the free body, you have 10 reaction acting up, 20 kilonewton down. When you draw free body, you don't use words like load and reaction and all because the body doesn't care which is the load, which is the reaction. They are just two forces. Again, after drawing this, instantly you draw your V of X and M of X. Always positive. Then satisfy equilibrium, very easy. V of X now will be minus 10 because 20 is here, 10 is here, 20. So you need a force here acting upward. This 10 plus this 10 must equal to 20. So you write it green with Vx, but the minus says it will be in the opposite direction. Very simple. So your shear, what do you learn from this? Your shear is positive from A to the middle and becomes negative from the middle to B. That's what you learn from this. And your moment will remain sagging, and you can write an expression. So 10 into X minus 10 into X because this is the direction and plus 20 into. So you have to write the whole expression 20 into X minus 2. When you expand it, you will get minus 10X plus 20. Okay. Actually, we kind of wrote the final answer, but as a beginner, you should write all the steps. You'll end up with this answer. And actually, it's nice to put brackets here and show that the whole thing has units of kilonewton meter. Please, these units are important. Shear force has units of kilonewton. Bending moment has units of kilonewton meter. You've solved it. That's it. But now you have one more section here, but don't waste your time. Here, don't cut a section from the left. That's stupid. Wasting a lot of time. Why don't you conveniently cut from the right side? Always when you see a cantilever or an overhang, go to the free end. That's it. Stay with the same definition of X, but the total length is 5. So when you come from here to here, this is 5 minus X. But there's no load on this section, and so there's no shear force. Now shear force should be drawn up when you cut the section. When you move from the right, it's pointing up and the sagging moment is 0. So this is obvious. You need not draw this because it's so obvious. And so finally you can write the expressions for shear force and bending moment. Whatever we got here, we write in a simple format. If you want to do this, now you're ready to draw the diagram. You'll find that BC has no shear, AB has a positive shear of 10 and I think some D or something should have been written here. So you got positive shear 10, negative shear 10, overhang nothing. This is a classic diagram, constant shear, but here there's a sudden discontinuity and a reversal in sign. And at that very location, you find your bending moment is maximum. Your bending moment, look at the expressions of bending moment, 10x. What does 10x mean? Linearly varying with x, but this is valid from up to 2 meters. So x is maximum at 2 meters, exactly below the load. You get 20 kilonewton meter, and so it rises to 20 like a hill, and then thereafter it goes down to 0 from the second expression. After some time, you will be able to do this easily. This is typically the behavior of a concentrated load. It causes a constant variation of shear changes sign wherever the load is acting, and at that very location, the bending moment is max. If you want in terms of formula, if the span of the beam is L and this load is W, shear force is W by 2, and the bending moment is WL by 4. That's a generic formula. Overhang and the deflected shape. Always do this when you get problems, even if the examiner doesn't ask you this question. This really shows your understanding. Simply supported beam will deflect like this. This is just like a rigid body attachment. So the moment is 0 here, the curvature is also 0 there, the radius of curvature is infinite. So this is just an add-on. It will, whatever slope you have that, with the same slope it will rotate. This is just an additional piece sticking on. It won't create any problem. Now I'll give you a simpler method, which practicing engineers use. We don't waste time. We have no time. We've got a lot of structures to design, build, construct, make money. So what do you do with this problem? Moment you see it, you throw away the cantilever, the overhang, the distraction. You put it back later. Now you throw it away. Then write down the reaction. Draw the shear force diagram. Draw the bending moment. Finito. That's what you do in fact. After some time. Beginning you do the other way. The fast way to do, draw the deflected shape. Now bring in this fellow and add it so that you find, okay, there's some lesson to learn from here. The shear force is constant in one half and the other half, numerically same value, but it's switching sign. And the bending moment is varying linearly. So there is a message to learn from this. And there's a relationship which we'll prove later, that the shear force is given by the derivative of the bending moment. So you have a line with a constant slope, the two positive slope, and that is your shear force. You have a linearly varying bending moment, but with a negative slope, that's your shear force. So there is a link, and not only that, where the shear force is changing sign, passing through 0, there you're hitting the peak in the bending moment. This is the curvature. The curvature is also having this shape, by the way. Why? Because M is equal to EI into curvature. So curvature is simply, if I ask you to draw a curvature diagram, simply copy the bending moment diagram and divide it by EI, assuming EI is constant. In fact, I should have asked you to do curvature diagram. Very simple. Radius of curvature is 1 by curvature. Now, what happens to this part? That's what happens, we know. So, easy. Now we'll ask another problem. Okay, problem with two overhangs. Earlier one overhang to hang you, now two, and students really get confused. This is symmetric, so life is easy. You find that if the load is P at the edge free end, then you can write down these equations. I didn't do any calculations. I want you to come to a level where you can even do this mentally. Let's do it. Let's say I cut a section, my X is measured from 0 to A. So I'm starting from the left. This is X, it's shown here. I cut a section here. Remember the direction of shear force, V of X should point downwards. So clearly V will be minus P in this entire stretch. And the moment, I should show sagging. The moment will also be minus, right? The moment will be P into X. I'll show you that also. So that's so I got minus p of x from 0 to a. Then when I come inside, you will find that I got p here, my free body another p here, so there will be no shear force here, right? So shear force is 0 in this entire stretch, and the bending moment will be p into x minus v into x minus a. And so you'll find that bending moment turns out to be constant in this region. You can show to be minus p. Minus means hogging. And this side you don't waste your time. Whatever you got here symmetrically, you'll get there. And so without much effort, you should be able to draw these diagrams. Shear force diagram is like this. There's no shear force in the middle region. And in that very region, the bending moment is constant. And where the bending moment is linearly varying, the shear force is constant at this end. Right? We'll derive this later, but the broad principle is here. This is going to stretch like a circle. Now I want to chat with you. Will this whole thing be a segment of a circle or not? Will this whole thing be a segment of a circle or not? Yes, it is a circle. Yeah, but someone has said correctly, only between supports. Brilliant. Why only between supports? Why only between supports? Your answer is correct. And I want to congratulate you for the correct answer. Look what's happening here. Only where you have pure bending, you will have a segment of a circle. This is impure bending. The impurity is the shear. So please note, in this region it's a segment of a circle. Here it's not. The radius of curvature is going to vary. So good answer. So let's look at this. The pure bending is going to be only in the middle region. And you can see that this tangent here is not matching here, but here in the region it's matching. Okay. Next question, what happens if I double the, okay, I double the load? Can you draw the shape? The shape will then look like this. Very interesting. Everything will be scaled. It's a linearly elastic problem. The deflection will be doubled. The radius of curvature, will it be doubled? The bending moment will be doubled. The curvature will be doubled. But curvature is 1 by r. So radius of curvature will be halved. Very interesting. Okay. Okay. Now we'll move on. When the load is doubled, the moment is also doubled, the curvature is also doubled, hence the radius becomes half. Now let's do a problem. Find the maximum safe load P if the permissible stress in tension is 40 MPa and in compression is 75 MPa. So I got a material whose strength, whose allowable stress in compression and tension are different. I want to use this material fully. I am applying the load P. What is the safe value of P I can apply? Very practical question. The cross section is given here. Now time is short, so you should go back to this question and work out the answers, but I'll give you the concept and move ahead. Remember the magic formula. Simple bending theory. M by I is equal to E by R is equal to sigma by Y. The E by R is useful if you want to look at deflections and curvature. Otherwise, throw away that E by R. So what are you left with? M by I is equal to sigma by Y. You want to find sigma. Sigma is given to you. So use this equation. And so you need property of I here. Remember, so for an I section with these dimensions, you know how to calculate it. I'm not going to spend time on this. Please do it. Find out the centroidal axis by maybe starting with the top fiber and you can have two areas, A1 with centroid at Y1 and A2 with its centroid Y bar 2, and find out the total area, do all these calculations. We'll assume you know how to do that. In this problem, Y bar is found to be 77 mm. Then use parallel axis theorem for each part A1 and A2, get the second moment of area, and you should get these answers. Okay, so I'm assuming you found I, and let's proceed. So the bending moment diagram we know how to draw. We know the deflected shape. We know also this is hogging, the opposite of sagging. The top fiber, that means in this T section, in the top line you have the maximum tensile stress, the bottom you have the maximum compressive stress. We don't know which allowable stress is reached first, because you can't put any load beyond that, you're not allowed to. So it makes sense to check out both of them. So if I say that the top stress, allowable stress is governing the design, then I should take M is equal to sigma top allowable divided by Y top into I. Incidentally, this IZ by Y top is section modulus, but I didn't write section modulus here, I took the whole thing. It's worth talking of section modulus when you have symmetric section, but here also you can do that, and we get M allowable to be, if you plug in the value, please note in tension the permissible stress is 40 MPa, so 40 you should put here, I is this and Y is this, so you get some capacity, 53.8 kilonewton meter. This kilonewton meter you can convert to load P by dividing this by P into A. So the moment here is P into A, the maximum moment is P into A. So you are actually getting 53.8 kilonewton, please note, that's a load. If you look at the bottom and the moment is governed by the compression, the tension at the bottom, then the top fiber is in tension, bottom fiber is in compression. Now you will use 75 MPa because that's the allowed stress, and then you recalculate this, that this is the distance to the bottom fiber from the centroid neutral axis. You get a lesser value, 44.9 kilonewton meter, or P will be 44.9. So which will govern the design? This will govern the design. Because if you put a higher moment than this, they are going to exceed 75 MPa. So the lower, this is going to govern the design, and that's the answer. So the P allowable is 44.9. We actually do tests like this in our laboratory. This is a test done in the structural engineering lab at IIT Madras. This is a reinforced concrete beam. You will see that the top fibers are subjected to tension. Concrete is weak in tension, so it kind of cracks here. There are two concentrated loads being applied here, PP, and you can measure strains and curvature and all that. So these are very simple tests to demonstrate. You'll find that here you have constant radius of curvature, but in these regions you don't. And there are diagrams available like this. You can see very nicely the radius of curvature being constant here. Here you will find that the radius of curvature is going to change throughout. You can see it here. It doesn't look like a segment of a circle. Here it looks like a segment of a circle. And here you can see the overhangs. It's going to be straight because it's just moving like a rigid body, but here it's curved. Very interesting to understand. So here you have a cantilever beam fixed here, subject to a load in between here. You'll find that this region is curved, but this region is straight because the bending moment is 0 here. Cut a section anywhere in this region, there's no bending moment.